So now we've learned what is modular arithmetic and we've understand the basic properties. And now we will talk about Fermat's little theorem and the Wilson's theorem. We start by consider a set. We call it set S, and set S is start from n 0 a 2a 3a and the multiples of a, and we also choose a prime p, such that p and a, the GCD of p and a is 1. They are co-prime, which means that p do not divide a. And we consider, what we consider is the set S elements divided by p, the remainder of the set element, the element of S divided by p. And we can have some example. We can first see when a is equal to 3 and p is equal to 7. We see that S is 0, 3, 6, 9, 12, 15, etc. When it divides 7, we get the remainder is 0, 3, 6, 2, 5, 1, 4. You can check it, and when we keep writing, you can check it yourself, and you'll find that it is periodic. The sequence is a periodic sequence with a period of 7. You can have them check yourself. And another thing, when we yeah, it is easy to explain why it is periodic, because for example, the ice element I times a, it should be congruent to I plus p times a mod p, right? It means that the ice element is equals to I plus p's element, which means that the sequence have a period of p. Yeah, and we can now look at the first p minus. We can now look at the first p element. If take the example of p minus 7, the first 7 element in set S mod 7 is here. Another key observation is that there's no repeated element, right? Every number less than 7, every remainder of 7 occurs exactly once. So we naturally ask ourselves whether this observation can be generalized. Indeed, we can prove this. We can prove that for a prime p, when S is equal to 0a, 2a, 3a, the multiples of a, while a and p are co-prime, we can see when this set is divided by p, the remainder of the first p element should be unique. It should be exactly the permutation of 0 to p minus 1. The set should be 0, 1, 2, 3, and p all over to p minus 1. How to prove this? We see if in the first p element, if there indeed occurs two element that is equal, we say i's element and j's element, which is I times a and j times a, if they are co-prime, if they are congruent by p, then we get I minus j is congruent times a is congruent to p, but it's congruent to 0 mod p. But we know a and p are co-prime, right? It means that p is divisible by p divides I minus j. and when p divides minus j, and at the same time we are talking about first p minus 1's element, which means that ij is smaller than p and greater or equal to 0. So i minus j is 0 or p or 2p, but I times j are all smaller than p, which means that I minus I and j are all smaller than p, which means I minus j cannot be p, and the only choice is 0, which means that I equals j, and so it is impossible for two elements in the first p minus 1 elements to be equal, and we prove that the uniqueness of S mod p, the first p elements remainder are unique. What this tells us is that we can write it in a more formal way. 0, we have we have p be a prime, and s be the set of 1, 2, 3. Now we neglect 0. We can neglect 0 because 0 times p is equal to 0, so we can neglect the 0 directly, and it won't affect the property of uniqueness. And we know that a times any a that is co-prime to b to p times s should be congruent to s mod p, which means the set of as, which is a2, a3, a p minus 1, they have those two sets have the same remainder modular p. And if the two sets are equal, we typically we can derive that the sum of the sets, the sum of the elements in this set, and the product of the elements in this set, and the sum of squares and squares of sums are all equal. It can also lead to many meaningful conditions, but now we can consider the product. We can consider sum, but sum does not give us many meaningful thing. It only tells us some trivial facts you can check yourself. But if we check about the product, we know the product of S is equals to p minus 1's factorial, right? And product of AS is equals to a times p minus 1, a to the power of p minus 1 times p minus 1 factorial. And this should be congruent to each other mod p, right? Look at this equation. It is very nice because p minus 1 factorial are co-prime with p because p is a prime. And this is very good because we can directly cancel p minus 1 and p minus 1 out, and we finally left a p minus 1 is equal to 1 modular p. This is the Fermat's little theorem. And now we can also observe the previous set of S. We see that for any as. A can be any integer. We have a times an integer. For example, a times x can be any integer from the set S. For example, b, and b should be less than or equal to p minus 1 and greater than or equal to 0. And we have this congruence is always true given a, we can always find there always exists an x such that ax is congruent to b. A very nice thing is that when we let b is 1, we have ax congruent to 1 modular p. And this is a very unique condition because it means that we have an inverse, right? In any arithmetic, when we given an a, we can time an integer. We can always find an integer x such that a times x is equal to 1, which is the identity. And that is very good. And therefore, we define x as the inverse of a mod p. Inverse of a mod p. What this gives us is that, for example, we can now we have for any a and ap coprime, we have an x such that ax is congruent to 1, right? Mod p. And this is very similar to the rational number, where for a given a, we can always find a minus 1 as the inverse, that such that they times a its inverse is equal to 1. And in this scenario, we write in modular arithmetic, we write the inverse x as a to the power of -1 or 1 to a. We can write these two forms. And this is very similar to the inverse of the rational number. We use the same notation in modular arithmetic. And it is very good because actually the inverse in modular arithmetic is similar to the inverse in fraction. The inverse of modular arithmetic behaves as like fraction. What this means is that when we write a to b plus c to d is equal to or is congruent to ad plus bc to b plus d mod p. It is not a trivial fact because actually this kind of notation implies ad plus bc times the congruence of bd. And it is equal to a times the congruence of b plus c times the congruence of d. And this is not a trivial fact. You have to convince yourself. And how can we prove this? And it is fairly simple because we can directly add because we know that when for example, in the rational number, if we want to add these two fractions up, we first times a b in the first fraction, and then times a b in the second fraction, and then add them up, right? And similarly, in modular arithmetic, we do the same thing, because as c times c's inverse is equal to 1, and b times b's inverse is also equal to 1. Sorry, we use d, and it is all the same, right? So we can expand the first term like this. We time d times d's inverse, and it is equal to 1, so we can time without any effect on the real value of this equation. So we get, here's what we get. We have a d and bd's in times bd's inverse plus cb times bd's inverse. And this is what we are looking for, AD plus CB times BD's inverse. And this can be rewrite as BD AD plus CB mod P. And this is very good, because if you can try some example, and you will find that this property makes modular finding inverse much easier. And this is how inverse add like fraction. Now we show that how inverse multiply like fractions. What do we mean by multiply like fraction is that a to b times c to d should be equal to ac times bd, ac to bd mod p, right? And this is also not a trivial fact, because if we write them, if we expand them clearly, it is a times b's inverse times c times d's inverse is equal to ac times bd's inverse, right? And yeah, indeed, this is much more easier to prove than the additive, because as I expand them, you can see that we can directly change the order of the element, and then we can regroup them. And we finally get our result, and we show that the inverse of a modular arithmetic also satisfy the multiplicative. And now we can have some proof, have some exercise to use what we've learned. What we want to prove is that if a does not congruence to 0 mod p, then a to the power of p minus 2 is congruent to a to the power of minus 1 mod p. How can we show this? It is very obvious that when we encounter those exponential that is near a p minus 1, we can think about Fermat's little theorem, right? Fermat's little theorem tells us this thing. And here's the inverse. So if we time an inverse on both sides, we get our result, because we if you want to write it stricter, you can say this and this, and a A minus A's inverse is 1, so essentially it is A P minus 2 to the power of P minus 2. So as a result, A to the power of P minus 2 is congruent to A's inverse mod P. And now we can further look at some more interesting fact about inverse. We still start from observing the set S. Set S, we can take an example. For example, P is 11. Set S is 2, 1, 1, 2, 3, all the way to 10, right? And if we find each of the elements inverse respectively, we can have 1's inverse is 1, is right? 1 times 1 equals to 1. 2 times 6 equals to 12, which congruent to 1. And 3 times 4 is equals to 12 and congruent to 1. 5, 9, 40, 45 is congruent to 1 because 45 equals 4 times 11 plus 1, 44 plus 1. And we may let's write everything out. 4, 5, 6 to see it clear. 10, 11, sorry, 10. And 1's inverse is 1, 2's inverse is 6, 3's inverse is 4, 4's inverse is 3, 5's inverse is 9, 6's inverse is 2, 7's inverse is 8, 8's inverse is 7, 9's inverse is 5, and the 10's inverse is 10. Let's observe some about let's look at these two set. The first observation is that there are two inverse that is the same as itself. The first is 1, right? 1's inverse is always 1 because 1 times 1 equals 1. And the other is 10. Except those two number. The other number always are not equal to themselves, right? We can prove this for a prime number P. We can see if a number A's inverse is equal to A itself, then A squared is equal to 1, right? And this means that A minus 1 times A plus 1 is congruent to 0, which means that either P divides A minus 1 or P divides A plus 1. And we know that A is smaller than P, so either A minus 1 is 0 or A plus 1 is P. So we get A can only be 1 or P minus 1. So we've proved that for every P, the 1 and P minus 1 are the only two elements such that its congruence is itself. Its inverse is itself. And all the other elements have a different inverse than itself. But we know, if we see it clearly, we see that the inverse, the two set of inverse are permutation of each other. This implies when we this implies that when we time these numbers together, for example, for 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9, we can always regroup those elements 2 by 2 such that those two by 2 such that those two elements are their inverse. For example, 2 and 6, we regroup them. 2 times 6. And then 3 and 4, we regroup them by itself and its inverse. And 5 times 9 and 8 times 7. All of them equals to 1, which means that besides when we consider p minus 1's factorial besides p minus 1 and 1, we have it must be congruent to 1. You can prove this. You can change 11 to any prime and the situation is essentially the same. So what is very well is that since p and p minus 1 are co-prime, we can directly time p minus 1 on both sides and we get this equation. And when we minus p on the right hand side, we get this modular equation. And this is what Wilson's theorem talks about. Wilson's theorem essentially implies two things. One is when p is a prime, we may change a little bit. If n is a prime, it's better. If n is a prime, we get n minus 1 factorial is congruent to negative 1 mod p. Mod n. That is, we've proved this. At the same time, if n minus 1 is congruent to negative 1 mod n, we can also show that n is a prime. This is a very rare standard that we can test for a prime number. This is a very rare standard, prime standard. Yeah, we won't prove it not here. You can check it on the internet, and all you can think of is by yourself. It's just do it in another direction. Yeah, and we can use Wilson's theorem to do some problem. For example, we want to show that we want to find the GCD, the greatest common divisor of n's factorial plus 1 and n plus 1's factorial. It is clear that we may consider a prime p if it is a divisor of both of these two numbers, and if p is less than or equal to n, p should be divisible by n's factorial, which means that p does not divide n's factorial plus 1. So for any given prime factor p that is smaller or equal to n, it cannot be the GCD of n's factorial plus 1 because p cannot divide n's factorial plus 1. So we can consider a p that is plus 1, because we know that if p is greater than n plus 1, then p cannot divide n plus 1's factorial, right? So the only possible case is p is equal to n plus 1. if p is equal to n plus 1, we can use the Wilson theorem, right? If p is a prime, then we have p minus 1's factorial is equal to negative 1 mod p. When p is equal to n plus 1, we can substitute and we get n's factorial is congruent to negative 1 mod p, right? And we see here the very nice thing is that we directly prove that p is divisible. P divides n's factorial plus 1, which means that p equals n plus 1 divides n's factorial plus 1. At the same time, we know that n plus 1 is divisible by n plus 1's factorial, which means that p is divides n plus 1's factorial, and we know that the GCD is equal to p, and p is a prime where p is equal to n plus 1. And we finished our question.